Welcome to Brain Vision.
We begin this question by following the hint. So remember that the maximum of interference on a double-slit experiment happen precisely at locations that satisfy d times the sine of theta being equals to lambda times m, where m is an integer number that can be equals to 0, 1, 2, and so on. Any integer will be fine. Now, note that we will have a very small angle in general when working with these fringes. Therefore, we can approximate sine of theta as being equals to theta, approximately, and theta has to be given in radians, so we can use this approximation. Therefore, d times theta is equals to lambda times m, which makes the angles of the maximum be equals to lambda times m divided by d. Therefore, let's call this lambda m. Therefore, the angular separation between two maximums, delta theta, is equals to theta m minus theta m minus 1, which is its neighbor. And this is equals to lambda over d times m minus lambda over d times m minus 1. We can write it as lambda over d times m minus m plus 1, and therefore the angular separation between two maximums is equals to lambda divided by d, as we had to show. Then, note that the minimums happens a half step between the two maximums. Therefore, the angular separation that we are looking for, let's call it delta theta max min. So the angular separation between a maximum and a neighboring minimum is equals to half the angular separation of a maximum and its neighboring maximum. Therefore, it is equals to lambda divided by 2 times d, as the hint asked us to prove. We can now proceed and calculate the separation delta y between a maximum and a neighboring minimum on the screen. This delta y is the distance between a minimum and a maximum. Note that we can extend this line to get a right triangle. Now let's call this x and this L. L is the separation between the screen and the double slit. With that, we can conclude that delta y is equals to x times the sine of theta. But theta is a very small angle, therefore we can approximate it as being equals to x times theta. But on the other hand, if the angle is very small, it means that L and x are very close to one another. So we can approximate x as being approximately equals to L. Therefore, we can further approximate it as L times theta. And we have now an expression for the separation that we wanted. Now note that theta here, this angle theta, is this theta, which is the angle between a maximum and a neighboring minimum. And we had calculated already what angle is this, but we had called it delta theta. So this delta theta is equals to lambda divided by 2 times d. Therefore, we can substitute this theta by delta theta to get the following separation. Delta y is equals to L times lambda divided by 2 times d. So this is the approximate separation between a maximum and a neighboring minimum at the screen. This result means that a lot of electrons hits the screen at this position on the maximum, but almost no electrons hit the screen at a distance delta y from this maximum, and this distance is given by this expression. Therefore, a lot of electrons will hit y equals 0, and almost no electrons would hit y equals to L times lambda divided by 2 times d. Keep this result in mind. Now we proceed to another calculation. We now proceed to analyze the behavior of the electrons at the slits. Now look at the following. Suppose that when passing through the slit, we know through which one the electron had passed. So we know if the electron had passed through this one or through this one. What does this mean with respect to the uncertainty in the y position of the electron when passing through the slits? It means that the y position of the electron is known with an uncertainty of d over 2. Why d over 2? Because if it was more than d over 2, we would have an overlap. For instance, if it were more than d over 2, this would be the uncertainty for an electron that had passed through the upper slit, and this would be the uncertainty of an electron that had passed through the bottom slit. Then, any electron that lies in this region can have passed through any of the slits. Therefore, this is why we must keep the uncertainty in the y position of the electron at the slits within d over 2 at most. Therefore, we have that delta y at the slits is at most d over 2, so it must be smaller than or equals to d over 2 if we are to decide by which slit the electron had passed. Now, this has an important implication for the y momentum of the electron. Remember of the uncertainty principle, which says that delta py times delta y must be bigger than or equals to h bar divided by 2. This means that delta py must be bigger than or equals to h bar divided by 2 times delta y. And this must be bigger than or equals to h bar divided by 2 times d divided by 2. The 2 simplifies, so delta py must be bigger than or equals to h bar divided by d. Note that this is the smallest possible value for py, because the delta y slits is at most d divided by 2. And the value that makes delta y the biggest one is the same value that makes delta py the smallest one. So, delta py must be at least equals to h bar divided by d. Keep this result. Finally, we can calculate what is the spread at the screen by using our previous results. The spread on the screen is given by the following relation. So delta y at the screen divided by delta py, the uncertainty in the momentum in the y direction, is equals to L divided by the momentum on the x direction. Therefore, delta y at the screen is equals to delta py times L divided by px. By plugging in our previous results, we get the following. Delta y at the screen is equals to delta py, which is h bar divided by d divided by px. And if you remember, the momentum is given by h times f divided by c. So the momentum is equals to the energy divided by the speed of light. But the frequency is related to the wavelength, so we can write it as h times c divided by lambda times c, because the frequency is equals to c divided by lambda. The c simplify, and we are left with h divided by lambda. And this is all multiplied by L. Then we get that delta y screen is equals to h bar, which is h divided by 2 pi times d times lambda divided by h times L. The h simplify, and we get delta y screen is equals to lambda times L divided by 2 pi times d. And this is our result for the spread of the electrons on the screen. But note the following. We had calculated what is the distance between a minimum and a maximum. And this distance is given by L times lambda divided by 2 times d. So delta y is equals to L times lambda divided by 2 times d. Now note that delta y is approximately, so it's almost equals to delta y screen. So what does it mean? So the expected distance between a maximum and a minimum is given by L times lambda divided by 2 times d. But on the other hand, the spread of those electrons is given by lambda times L divided by 2 times pi times d. This is only a little smaller than the other result for delta y. So what does it mean? It means that instead of piling up on maximums and being almost no electrons at the minimums, the electrons would instead spread over that distance between the maximum and the minimum. That distance on our drawings is the following. So this is the distance between the maximum and the minimum. In order to actually have a maximum and a minimum, we must have a lot of electrons hitting this position, while almost no electrons hit this other position. But if we know through what slit the electron head went through, then they will spread out over another distance. They will spread out over a distance that's given by lambda times L divided by 2 times pi times d. So this means that instead of having this interference pattern, it will be destroyed because the electrons will spread across this range instead of getting piled up around the maximum.